is Lorenzo Demaria on identifying the stellar population behind interstellar clouds for ice mapping the distribution of solid material in star-forming regions. Floor is yours.
Yes, thank you very much. I am Lorenzo Demaria from the Open University, a PhD student. In the past few days, we have heard a lot about molecular clouds, but today I wanted to give you a different and complementary view of them, thanks to ice observations. So first of all, I will present to you why we care about molecular clouds, specifically why ice is. Continue on to how we do the observations, and then finally, how do we analyze this observation in order to extract as much information as we can. So first of all, as we all know, molecular clouds are precursors of stellar systems. Therefore, understanding their molecular budget can help us link it to the stellar and then further planetary formation. Why ices specifically? That's because they form the vast majority in mass of the condensable matter. In fact, for instance, water is the second most abundant molecule in the ISM, right after H2. In fact, we are able to see lots of water, but other common molecules like CO2 and CO as well in molecular clouds in ice form. We don't really need to know how these ices look like, just know that they're very cold, around 10 kelvins. They're very small, they absorbed on or deposited on ice grains. So we cannot see them in an emission, and we must see them in absorption against an emission background that could be embedded in the molecular cloud, like a YSO, or a star or a galaxy in the background. So how we do this observation, we could go and look at each line of sight one at a time, but that would take forever. If we want to understand the complex distribution, the spatial extent of the ices and their distribution, we need to do a better observation. So that's where the wide-field slitless spectroscopy technology, the observing mode, comes in, thanks, for instance, to JWST with NIRCAM. So here we are able to concurrently observe a lot of lines of sight and their spectral information at the same time. So this is what these observations looks like. This is just one frame obtained by James Webb. Here, each one of the bright lines, it's one spectrum which is being recorded on the CCD. Thankfully, I don't have to do the extraction of the information because there is a code that does that for me that was developed by my predecessors. It's very complicated because there is a lot of source confusion as well. But this is an example of an observed spectrum we get with James Webb. Now, here there is a lot of information that we don't necessarily care too much about because on top of the ice absorption, there is a problem because we do not know anything about the background source. We don't know anything about their population. We don't know really the extinction. We have a relatively high spectral resolution. So all of the little lines you see in the spectrum are real information. They are photospheric lines, or they are spectral features of the source. So we cannot just remove them without knowing them. And finally, we have thousands of lines of sight, as you can see here. Each one of the black dots is one line of sight that we're able to image with James Webb. This is in particular the Chameleon-1 cloud. To show that we don't really know anything of the sources, all of the other dots and stars are stars observed by either Gaia, TUMAS, or WISE, and out of all of the 3,000 line of sight we have with James Webb, only 120 match, and in most cases we have only partial photometry or very large errors. So, similar to what we have already discussed a lot today and yesterday, this is also another inverse problem because we have the observation. We want to understand the parameters that create this observation, the physical parameters. So what I have done, what I am doing in my PhD is try to simulate this observation in order to be able to extract the ice information we care about. Zooming in, first of all, we need to understand what is the source. I have limited for now my simulations to just stars, background stars. That's because they cover over 90% of all of the lines of sight anyway. These stars can be modeled using their stellar parameters like surface temperature, surface gravity, metallicity. they will be at a certain distance, which will obviously influence the flux that we are able to observe. Then the light that is emitted by these stars will go through, like a cloud, will go through the ISM in general, so it will suffer some dust scattering, usually explained by extinction laws with other parameters like AV and RV. There will be some dust absorption, but that's usually outside of the spectral range that I'm interested in, which is between 2.5 and 5 microns. There will be some gas emission. Again, that's usually very thin lines. And then the ice absorption, which is what we care about. So I'm not simulating them so that I'll be able to get them from the residuals. And finally, there is all of the instrumental effects, because the instrument will have some throughput effects due to electronics, optics, and the detector. But thankfully, thanks to the sensitivity curves provided, the extraction code already accounts for that. The only thing I need to understand is the spectral resolution, because I need to downsample my synthetic spectra to the same spectral resolution, as well as apply the filter cutoffs where necessary. So, as you can see, there are a lot of parameters involved, and in order to better understand the simulation, since a lot of these parameters are degenerate with one another, I need to understand how they influence the spectrum and what are the physical, sensible limits that I should apply to these parameters. To do so, I've investigated the background population. Now, I say we don't know that behind the cloud. In fact, as you can see, this is all the Gaia stars around Chameleon-1. Behind the cloud, so behind the black dots we have, there is almost no stars, but we can safely assume that the population is going to be similar around the cloud and behind the cloud. So I've analyzed the one around it, which is less biased, since Gaia observes in the visible. They have done a lot of research, a lot of studies to understand what are the stellar characteristics of these stars, as you can see in the plots on the right. We have a stellar temperature that range between 2,500 Kelvin, which is M dwarfs, up to 7,000 Kelvins, which covers all the way to the G stars. Brighter stars are a lot less common, so I think we will probably exclude them. As for surface gravity, most of the stars are in the main sequence, so between 3.8 and 5.5. And finally, metallicity, since we are looking relatively away from the galactic plane, we are also expect a slightly subsolar metallicity in the stars. So to understand how they change the spectrum, here I've zoomed in a bit. The main parameter in this case is going to be the temperature, which vastly controls both the overall flux that we observe, but also which molecular and atomic lines are present in the spectrum. As for the surface gravity, it mostly regulates the overall spectrum, the overall flux that we observe, while metallicity has only an impact on the on the lines that we observe in the spectrum. Here, in fact, the offset is artificial because it almost has no effect on the total flux. Continuing on, the extinction also has an effect. In particular, it has different effects at different wavelengths. So depending on the values that we have for AV, which is the extinction in the visible, and also for the RV, which is a scaling factor between the reddening, the color excess B minus B, and the extinction in the visible, we are able to essentially correct for the different extinction. Usually higher values of RV also correspond to larger dust grain or dust accretion, which is also what we see in our data, where most of the lines of sight will have the blue end of the spectrum much more extincted than the red end. Oh yes, just another thing to help us constrain a bit the extinction. We have used the Herschel data from the Gold Belt survey. As you can see, our data is roughly in the red square in the plot, where the extinction value varies between 5, give or take, and 50 AV. Now, this comes from a simple conversion factor between the H2 column density and the extinction in the visible. So it's prone to have a lot of uncertainty in it, but it can help us give just sensible prior to our simulations. Finally, the distance is also another key parameter. By studying where we're looking at, in the case of Chameleon-1, we're looking away from the galactic equator and also away from the galactic center, meaning that since we're looking away, the line of sight will at some point exit the Milky Way. So at roughly 1,200 parsecs, we are outside of the thin disk of the Milky Way, and also as shown by the Gaia data underneath, after roughly 2 kiloparsecs, we see almost no stars at all. That's because we are outside of the Milky Way. For all of you who do extragalactic observations, you all know that looking away from the galactic equator is the best to see a lot of galaxies. Pre-launch, we had thought that we would see roughly 20 galaxies in our field of view. Unfortunately, the number was much higher, meaning that we had to count over 300 of them, and then we gave up. But we were also able to see one supernova in one repeated observation we did. So a lot of happy accidents, I would say. Anyway, these are the parameter limits that we have chosen. It's not really interesting. So one thing, the distance has a lower limit because 200 parsecs is the distance from us to Chameleon-1. So we do not see any foreground stars. And even if we were seeing them, they would have no ice up because the ice will be in the molecular cloud, which is behind them. Finally, this is some observation that we have done. For now, I have done some manual matching with only a couple of these lines of sight, so I do not have yet a proper fitting algorithm. This was done as a first look to see is it worth doing this proper SED fitting. As you can see, there are a lot of lines in our spectrum and a lot of lines, the corresponding lines to the matched SED as well. By zooming in, we can see three very broad ice features here. First of all, the OH stretch at 3 microns, the CO stretch at 4.26 micron, and the CO stretch at 4.7 microns, give or take, corresponding to water, CO2, and CO. All of them are fully saturated, meaning that it reached the lower flux that James Webb is able to observe. By zooming in a bit on some particular regions of interest, we are able to detect some weaker minor ice features, like, for instance, 13CO2, 13CO, which is very important to study because understanding their column density can give us information on the isotope ratio in the molecular clouds, can give us some information regarding the different fractionation processes that these two isotopes go through, and therefore give us information on the chemical history and the chemical processes that undergo in the molecular cloud evolution. We're also able to see some other weaker ice features like the dangling OH at 2.7 microns. We have the CO gas grains interaction together with the OCN minus. And finally, we are able to either detect, confirm, or deny some detections for some minor ices. For instance, a first analysis that was done on this data claimed a tentative detection of CH4, methane, and OCS, which could be there, but by doing a proper fitting, we see that it's not really statistically significant, and the error could have been done by taking a very simple local baseline, like a polynomial baseline, also due to filter effects for OCS as well, since it's towards the end of our filter. So, comparison with published data. As I said, this was only a manual fit. So I looked at the spectrum and picked which parameters best explain our observation. But again, I am not perfect. I never will be. And also our stellar parameters were from a grid, which is relatively sparse. So even if I wanted to, I could not select, for instance, better temperature or surface gravities. So there needs to be more work done on it, but at least the comparison with other papers, in particular the Daltois one, which did a proper SED fit for these two stars, shows that we are in agreement, in particular with the stellar type. Now, they have done it. Why can't we do it for all of the others? Well, they only analyze these two line of sight. So even if you take a month or two to study two of them, it's fine, but we cannot do it for 30,000 lines of sight. So overall, I would say this is a good method. Try to do an SED fit can help us understand, in particular, the weaker ice feature, where otherwise local, simple baselines would introduce a lot of errors, which are not negligible. Again, it's not a proper fitting. I've already investigated some possible ways to solve this problem. If you have any ideas, feel free to let me know. One of them in particular used Gaussian processes and exploring the parameter space with gauge sampling. Another one, this one was focused on white dwarfs, so different field but similar process overall. Use a hierarchical Bayesian model that we've already seen in the past few days as well. Overall, key important thing is that the objective is not to fit the best possible SED to one source, but we want to find something which finds the optimal fit for most of our thousands of sources, even when the spectrum is partial, because maybe the star was towards the edge of our CCD, so we don't have the full diffracted light, or there is no other photometric information, since for most of our lines of sight we have no other service that we're able to see them. So thank you for your attention. If you have any questions, information, I'm happy to answer.
We have time for questions.
Thank you for your very nice data. You said you made a manual fit, so what do you need to make an automatic fit?
Okay. The problem was that at the beginning we didn't really understand how, we didn't really know what were all of the parameters that went into doing the fit. So the reason why we started with a manual one was to actually see, are we able to actually properly simulate our observation, or is there something missing that we should introduce? Because the other two papers that I mentioned there that do something similar, I was only able to find them much later on in my PhD. So at the moment, it's literally just the next step to do the automation. So hopefully soon we will have some data. The problem was that, again, in particular for the stellar models, as I said, if I were to compute them manually, it would take weeks, because it does take them weeks to just create one spectrum, because there is all of the atmosphere code and then all of the radiative transfer codes on top of it. So what I'm using at the moment is just a grid of spectra, which is relatively sparse. So I was also trying to find a way, okay, am I able to interpolate correctly or not? So that was the reason.
Any more questions? We have time for one more question.
Very nice. You mentioned that there are some lines on top of the spectrum that you said that they come from the cloud. Is there any information there? I mean, that's a very rich data set. So
yes. Which lines? Do you remember exactly?
Well, you said in the spectrum there were a lot of thin lines.
Oh, okay. Okay. Well, the one in gray, first of all, is just the error bars. As you can see, some regions have much higher errors. That's due probably to some source confusion, because we have many overlapping diffraction lines in our CCD. All of the weaker lines that I mentioned, I suppose all of these little lines, either they are some very weak ice features, for instance, we have here 13CO. We might have some very weak other, CO2, other weak CO2 isotopes, either due to, mostly due to the oxygen, or they are photospheric lines.
Oh.
So they are lines from the star itself.
Nothing from the cloud.
From the cloud, we might have some weak gas emission, but I have not done a proper fit. I'm not technically an astrochemist, so I don't really know this. But if you have any particular idea, obviously.
Well, it would be interesting if there are gas phase features, because you will see at some point when you start creating the grains, basically putting that gas into the gases.
We are able to. I don't think we are able to fully see them, because they should mostly coincide with also the ice feature, and the ice feature absorption is much stronger than the corresponding emission. So, and also the emission would be much thinner. For instance, for CO2 and CO, it would be a very thin line, which is completely overwhelmed by the ice absorption. Also because, for instance, in this particular spectrum, the column density of the CO2 and CO is 10 to the 18. And for water is like 10 to the 19, give or take.